Okay, so for statistical hypothesis, for the one that we use most, which is t-test and f-test, we normally involve the null hypothesis that the statement contain equal sign. So that's why I put it here, because both two tests actually mainly they compare the errors, and they just want to make the errors to be between two cases to be like virtually zero, or there's no change. So that's why I say that the null hypothesis is a statement that contains the equal sign. But in general, okay, in general, it might not always be equal. Okay, so what I want to make sure that you know here is that basically the null hypothesis is something that we want to prove. Okay, more or less, null hypothesis is one thing, the one that you want to the one that you ask is the question that you ask, or the statement that you want to ask. Okay, the point is that, okay, I just let me put this down. It is the thing that you want to ask, or more or less is the question point. Okay, looking at things like this. And alternative hypothesis is something, any other thing. Okay, any other thing apart from what you want to ask. Okay, so it's not always an equal sign in that sense, because you could ask, I mean, you could have some statement, something else, okay, which may not represent the equal sign. For example, if you want to see that the average salary of this company is more than 30,000, okay, the null hypothesis would have been equal sign, would be it will be high, more than sign. Okay, and but the point is that when we do a statistical test, we want to disprove that sentence. So in the question, in the statement that I just said, the H node, okay, the H0 would be that if the average, okay, of the salary is more than 30,000, the HA or H alternative will be the average salary will be less than or equal 30,000. The point is, if you want to say whether the null hypothesis is right or wrong, you would accept or reject that one. The process of doing so, you want to say that this one is not right. Okay, in order to accept that one. So it can be confusing. It can be confusing. It is something that we want to prove, but we have to disprove it to say that it's right. Okay, so that's how it goes for statistical hypothesis. So the point that I want to make a little bit of correction here is about the equal sign things, because most of the time equal sign is what we have for null hypothesis in our work, but in general, it is the thing that you want to ask. It is the statement that comes up. Okay, and alternative hypothesis is other thing else. Okay, so that's what I just want you to sort of like know before you are having more confusion on this stuff. Okay, and the other thing Okay, the other thing that we talked about yesterday, so that's why the hypothesis testing is the test for the rare event. Okay, so we have to disprove the hypothesis. So we just make sure that the null hypothesis is not something that it's just the random thing that happened. Okay, so that's how it goes for statistical tests. Okay, I'm sorry it seems confusing, but that's how it is proceed. Okay, and maybe, and another thing I want to emphasize a little bit more. I thought I didn't make it very clear yesterday, was that it's about the p-value. Okay, the p-values. Okay, yesterday I say that the p-values that you might see in the paper is related to alpha, which is the significant level. Okay, and I know that most of us say that if the p-values is normally when you see if the p-values is less than 0.05, so you say it's significant. Okay, so that's how most of us go. The point is that why is it has to be less than 0.05? So normally if it's significant, that means that you reject no hypothesis, that you reject H node and say that it is correct. Okay, so these values of 0.05 is actually come from the alpha of 0.05. So that means that if you are saying that if p-value is less than 0.05, then things become significant. It means that you are saying that you are testing the hypothesis at significant level of 0.05 or at 95% confidence level. Okay, so that's why when you say, okay, if p-values, okay, equal 0.03, which is less than 0.05, okay, that thing becomes significant. That's how you go. But if the p-values is 0.12, it is, so it become insignificant. That's how you see most of the time in ANOVA table, right? The point is that if you are testing it at different level of significant different significant level, for example, if you take these p-values, you get the p-value of 0.03, but you are saying that you are testing at alpha of 0.01. Okay, so at 99% confidence level. That means that your p-value is higher than your significance level. So it's not become significant anymore. It will become insignificant in this case. So p-value tells you the probability values, but in order to say whether it's, I mean, whatever you test is significant or not significant, it depends on the level of significance that you are testing at. But most of the time we use alpha of 0.05 in testing. That's why you always think that p-value of less than 0.05 is the key. Okay, so you need to know this stuff as well, that it depends on the significance level that you are doing your test with. So that is the point about p-values that I didn't make it clear yesterday. Okay, now let's see about the hypothesis testing, right? The statistical testing. I have in this slide the example of the testing on the t distribution. Okay, this thing can be applied to any type of distribution curve. Okay, and normally when we are doing statistical testing, we have to determine whether the test that we want to do is one tail test or two-tailed test. Okay, with the word tail, okay, it is being the tail of the curve. So this one is the tail of the curve, and that one is also the tail of the curve. Okay, and let's see the example of the test as the confidence level of a significant level of 0.05. Okay, for one tail test, you are interested in the area, whether on the left or on the right tail of the curve. Okay, see this first, and 0.05 is the percentage, is 5% of the total area under curve. That's how the thing goes. It tells you that it takes 5% of the total area under the curve, whether it's on the left hand side or whether it's on the right hand side, if you are doing alpha of 0.05. Let's say if you're doing alpha of different number, for example, if you are doing alpha at 0.01, so that means that you are interested in area only 1% of the curve, which is where I put the red things in here. Okay, and if you are doing the test at alpha, a different alpha of 0.10, that is another thing, right? Okay, so that means that you are interested in the tail that takes about 10% of the curve. Okay, so that would be 10% of the curve. So alpha will tell you the area, which later on you will see that is the rejection area, okay, of the test that you are doing. Okay, and if it is a two-tailed test, okay, when you are doing two-tailed test, you have to divide it. Okay, since this is two tails, that means that the 5% has to divide it between the left tail and the right tail. So in the case of alpha of 0.05 or the area 5% under the curve, okay, this area, the black area that I highlighted green here, each become 2.5%, because this one is 2.5, that one is 2.5. You sum them up, you got 0.05, okay, which is the alpha of 0.05. Okay, now doing one tail or two tail test depends on the size of alternative hypothesis. Okay, depend on the size of alternative hypothesis. So that's what I want you to think about. Okay, that's what I want you to think about, because the point is that you see in the area of accept H node and reject H node. Just looking at this thing first. Okay, so the size of the alternative hypothesis we said. Now let's see some example of the case where we decided whether we want to do a one-tail test or two-tail test. Okay, let's see this example. Okay, there is two questions here. Okay, so if you develop a new drug, okay, this is the first question. Think about it while I'm talking. If you are developing a new drug, okay, and you believe that this drug is better than the old one, okay? Whether you want to do one tail or two tail test. Have a guess, okay? Have a guess. Type down your answer if you like, okay? โจทย์ข้อหนึ่งถามแค่ว่าเราจะทำ one tail test หรือ two tail test ดีนะ ก็คือแค่ถามไอเดียให้ตัดสินใจนะคะ ก็คือถ้าเราพัฒนายาตัวใหม่ แล้วเราเชื่อว่ายาตัวนี้ต้องดีกว่าตัวเก่าแน่ๆ แล้วเราอยากจะเทสเนี่ยว่ายาตัวนี้ดีกว่าตัวเก่าแน่ๆ เราจะทำ one tail test หรือว่า two tail test ลองเดาก็ได้ค่ะ ลองเดาดูนะคะดีกว่าในที่นี้ก็คือ effective กว่านะคะ อย่างเช่น เอาเป็นวัคซีนก็ได้อะสมมุติว่าคุณ develop new วัคซีน แล้วก็เอาเป็นวัคซีน mRNA ก็ได้ เพื่อที่จะทดสอบว่า NIMA เนี้ยวัคซีน NIMA เนี้ยได้ผลดีกว่าวัคซีนเชื้อตายหรือว่าวัคซีนอะดีโนไวรัสที่เป็นเทคโนโลยีเดิมเนี่ยก็คือถ้าเราเชื่อว่ามันดีกว่าเราจะทำ one tail หรือว่า two tail test ลองเดาคำตอบแล้วก็ลองลองพิมพ์มาในแชทดูค่ะว่าเราคิดว่าเราจะทำ one tail หรือว่า two tail มีใครจะเดาไหมคะให้คิดถึงว่าเวลาเราพูดถึงว่าดีกว่าแย่กว่าหรือว่าเท่าเดิมเราต้องการเทสว่ามันดีกว่า okay okay there's people say two tail some say one tail okay 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 it's easy to think that if it is better than existing drug you it's definitely you have to do one tail test right the point is if you look at this question okay you see that it says that you believe that the drug is better okay so the drug is better has more is more effective in many ways okay than the old one okay so it's better so the better is the more than side right that's what we are thinking there's a chance that it is better than the existing drug okay so this better you are thinking of this side okay the point is that the answer to this question is that you should use the two-tail test okay because with the two-tail with the one-tail test what you will miss is you will miss the testing or the case where the drug is less effective okay so because when you are doing the test You want to test if the drug is better. Okay. Other alternative thing would be the drug is as good as the old drug, and is bad, is worse than the old drug, because the point is you believe that the drug is better. So if you do one-tailed test, you might miss the case where the drug is less effective. Okay, so that's how it goes. Okay, that's how it goes. And so that means that in this case, your null hypothesis will be the existing drug is better, and the alternative hypothesis is equal. Hold on. So in this case, hold on. It's in this case, the H node is saying the drug is better, right? Because you believe that it is better, but alternative hypothesis, that was two things, right? You think it's not better. The point is you have to include that it is worse than the old drug as well. Because if you do one-tailed test, you might just say that it's not better or it is worse. Okay, so it is to end of the story. Okay. Another question. Okay, another question is similar. Okay, you are developing a new drug, and that is cheaper than the existing drug. Okay, note that it is cheaper. Okay, and you also think that it is not less effective. Okay, what do you think in this case? Okay, it's cheaper and it's not less effective, so it is as good as. Okay, so do you think one tail is enough? Yeah, this is just the idea of statistic test first. Okay, you don't have to think so far that, hey, how am I going to do this or to do that? Just to get you some idea of how the one tail and two tail could tell you. Okay, what do you think? What do you think? Yes or no? Yes is one tail test is appropriate. No is one tail test is not appropriate. It could be the two tail. Okay, just yes or no. New drug, cheaper, and you think that it is not less effective, is as good as. As good as the new drug. One tail test is okay, yes or no? It's just like, what do you want to test in this one? And when you say it's not less effective, what does it mean? And whether it's enough to do one tail test. Okay. One tail test. Okay. There was no and there was yes. There's a no. Okay. So no means that you are thinking that you have to do two tail test. Yes means that one tail test is enough. So in the second question, since you think it's not less effective, okay, not less effective is equal to more or more, right? So one tail test in this case is enough. Okay, because when you say not less effective, your edge node could be equally effective. Okay, your edge node could be equally effective and so edge nodes would be equally effective or better. And your edge alternative is less effective. So it's one tail test because your alternative is only one is only one case. Okay. Right. So okay. Maybe you think that is the factor of the price, okay, will get into the decision of something, okay? The point is that this one indicates that this one has the word cheaper. That means that if it's not, if it is not less effective or if it's as good as the old drug, you think it's good already because it's cheaper. Unlike the first case where you are developing new drug and you think that new drug is better. So you neglect the possibility that it is equally effective to the old drug. Okay, but the question 2 indicate that it is cheaper. So that means that, I mean, if you develop new thing, two things that might have come in mind if you want to put it in the market is that it has to be more effective, right? Because it's new, right? The point is, if it is cheaper and as effective, it is still a good point to get into the market because it's a new drug, it's equally effective, but it is cheaper. So it's better, it's better thing. Okay. And you are developing new drug. How do you know whether it's cheaper? Because you have to come into that conclusion already, that it is cheaper. So the cheaper in this case say that it's not less effective. I'm going to take it that it is cheaper. So even though it has the same effectiveness, I'll accept it. But the first one say that it has to be better. Okay, so it's just the factor to say that even though it is not better, but it is cheaper, I'll accept it. So that's why your edge node could be equal, the quality, the effectiveness is equal or better. Okay, but the thing that you want to become alternative hypothesis is that it is less effective. Okay, so go back into that one. That one edge node will be to say that the drug is better, correct? And your edge alternative would be that it has an equal effectiveness and less effectiveness. So So it's the two things here at the alternative hypothesis, then it becomes the two-tailed. Okay, one thing here become a a one-tailed test is enough in this case. Okay, so that is how the thought has come about making the hypothesis. Okay, let me see if I and another point that I could make here is that remember when I said that in our case it's all most of the time that the null hypothesis will be an equal sign. Okay, because in the test that we are mostly do is we are mostly if we are varying something or to see whether the deviation is different, it is something that we have something like is value number one is mu plus the error, okay, and value number two is that mu plus error number two. The point is that in most of the time in our case, we want to prove whether these two values are different. So we compare if this one equal to zero. So that's how it goes for our edge node. So that's why I say it's the equal sign comes in most of the time in our case. So it actually depends on it's actually depends on the way you set up your edge node or HA. Okay, and it could be difficult, but the point is I want you to know that okay, edge node and edge alternative is something that comes whenever there are statistical tests, just that sometimes you don't make the awareness. Okay, you don't have the awareness of having edge node and edge A. You only see the p values and you only see, yeah, most of the time you see the p values. Okay, but before you get to that p values, every test has to have their own edge node and edge A before you get into that p values. Okay. All right, and the next slide, okay. The next slide is something about accepting or rejecting edge node. So in statistical analysis, okay, in hypothesis testing, of course you have null hypothesis and you have alternative hypothesis. Okay, the main thing of doing a statistical test is going around null hypothesis. So you are doing the test whether you want to accept or reject null hypothesis. Okay, alternative hypothesis is something else that doesn't include in null hypothesis. But when you are doing tests, statistical tests, you are proving, you are finding ways to say that you are going to accept or reject edge node. Okay, if you are accepting null hypothesis, the easiest way to say is you rejecting the alternative hypothesis, or if you are rejecting null hypothesis, that I mean, in the sense you say that okay, you accept another one. Okay. In a true statistic term, it is not that simple. Okay, but I'm not going to go through it right now. Okay, because unless you want to do some more explanation about why you're accepting this, but why you could be wrong and things like that. So it is something that our question. Okay, so just understanding that when we are accepting edge node or reject doing the test is trying to accept, finding the way to accept or reject edge node. Okay, so in any distribution curve, okay, this is a symmetry distribution. The same principle apply to any distribution curve that involve the hypothesis testing. Okay, so in under the curve, okay, and under this curve, okay, we say that the area is 100%. Okay, just like what we had there. Okay, under the curve, the area is 100%, and the value of the distribution goes along these values. Okay, and when you are doing hypothesis testing, you have to do it at a certain confidence level. Okay, the general case, if they don't say anything about the significance level, it most of the time is 0.05. I think all the statistical software that you use have this value set up as the basic values anyway. Okay, so that means that there was two area. Okay, two area that identify the cutting from its critical values. Okay, the area that goes beyond critical values, okay, both of the side of the critical values, is the area of rejection. So it's area that you, if your critical values falls into this point, okay, on the axis, that means that it falls within the rejection area. So that means that you have to reject edge node. Okay, it means area of rejection means that rejecting edge node. It doesn't mean that accepting alternative, but it is rejecting edge node. So it said that there is enough evidence that there is enough evidence that no hypothesis is not correct and is somehow acceptable to say that alternative hypothesis is right. That sort of thing. Okay, that sort of thing. So the critical values here is actually depends on the type of test, okay, that you do. So if you are doing F test, you will have F as your critical values. If you are doing T test, you get T, the value of T, as your critical values. Okay. For example, if you are doing F test and you are saying that for the test that you are doing, you have the F value of 3.14. This is a makeup values, okay? Okay. The critical value for the F is 3.14. And based on your data, you calculate also the F. Okay, let us see. So it's F. we have to be 2 DOF, degree of freedom. So 3.12, which is this point. If you are calculating the F values based on your data that you are doing the experiment, and your F values is less than 3.14, okay, maybe you have 2.8. That means that it falls into the area where you are, it falls to the area where you are accepting edge node. So you accepting the edge node. But if you are doing calculation and the value falls here, probably about 3.3, this point, okay, lies into the area of rejection. So you are rejecting edge node, okay, and saying that alternative could happen. Okay, now this is the basis of how you are rejecting or accepting edge node. What about the p-values? How the p-values come from, right? So like I said earlier, that the p-value itself has to compare to alpha, right? Okay, has to compare to alpha. Let me clear this screen a little bit, okay? Maybe I'll leave it like that. You're just choosing different color, okay? So the p-values is more or less the area that cover from the point that you're calculating. So for example, okay, the p-value of 0.05 in this case, where we have alpha of 0.05 is the area, the shaded area that you see in the graph. But that was from, that area is from the standard values of the F distribution. For example, if this is the F distribution, but this one is more like T distribution rather. But when you are calculating things out, and for example, if this F, you get F of 0.33, okay? So the p-values that you get from your experiment, you know that it will not be the shaded red area anymore, okay? So it is the area from this point that you calculate, which is 3.33, goes from this one. So that means that the area that you get from your experimental data lies within the area of rejection. So with that area, you can say that you reject edge node and make H1, and accepting what H1 say could be correct at 95% confidence level. Okay, that's how it goes. So that's why it says that, okay, if you are making the statistic test at alpha 0.05, so if your p-values is less than 0.05, then actually you reject edge node and say whatever the alternative hypothesis saying. Okay, so when you are seeing things in papers, okay, when you are seeing things in papers, especially when you are doing ANOVA, okay, when you see ANOVA table, you have p-values, and then if your p-values is 0.001, okay, you say that you will see that it say that it is significant. So it doesn't matter what it said here. You say that, okay, this is significant. Okay. So being significant here, okay, means that it calculated already the percentage of the area, whether it falls into the area of rejection or accepting edge node. And being significant, as it says, means that it falls into the area of rejection. So you say that edge node is not correct and edge alternative is accepted. is somehow could be accepted. Okay, so that's how it goes about the area of rejection and the area of acceptance node. Okay, the similar thing happens with one-tail and two-tail test. So I'm not going to repeat the two-tail test. Just that if you are doing alpha of 0.05, okay, if you're doing one-tail test, alpha of 0.05, the 5% of the area lies in this area. But if you are doing two-tail test, but your two-tail test is alpha of 0.05, so it's 25% here and another 25% here. Right. And okay. Actually, most of the lecture here assume that you have some background knowledge, okay, about a statistical test to some level from your undergrad degree. Okay, so if you don't get anything about this thing at all, maybe you could ask. I'll see if I could explain for those of you who don't actually have any idea at all. Okay, but anyway, okay, just let's finish the lecture here first. Okay, so when we are conducting a hypothesis test, the first step that we need to do, if you want to test something, okay, if you want to test something in terms of statistics, you have to set up the alternative and null hypothesis. You have to you want to see whether the errors from changing the level of this factor actually affect the response or not. You need to understand what alternative and null hypothesis you are to make, or at least if you are the user of the program, every time there is a p-values, okay, there is one test there. So in your ANOVA table, you might come up with like 10 tests, and each test has its own alternative and null hypothesis. Okay. The second, okay, I would say something like this. Since most of us probably see from reading the papers, but you can apply to your own research as well. So whenever you see the hypothesis testing, the p-values, the f-values, the t-values, whatever, first question that comes to mind is that what are the null hypothesis and alternative hypothesis? Okay, by knowing the both hypotheses, when you explain the results, okay, if you happen to use it in your work, you could explain the results that if this thing happened, that means what, okay? The next step is you have to ask whether what is the significant level that the test has performed, okay? So it could be alpha 0.05, 0.1, or 0.01, okay? But the general case rule of thumb is alpha 0.05. Then select a statistic and distribution to be used, whether you want to do a t distribution, or it has to be f distribution, or it has to be chi-square distribution. It depends on the type of question of the case that you want to test. Okay. And since selecting the distribution, then you know that what statistic and critical values you are going to have to calculate, whether it is the t values, okay, whether it is a t values, whether it is a chi-square values, whether it is the f values that you have to calculate. That is the test statistic. Okay, And you need to know that under your situation, what are the critical values of this stuff? Okay, so like I gave you example earlier, the critical value could be 3 point, which is F, I would say F crit is 3.14 in my previous example. Okay, if the F crit is 3.14, and you have to calculate your own from your work. Okay, and if you get it to 2.6, that is when you started to decide whether you would accept or reject your null hypothesis. So if you are using F statistic, okay, so it's F distribution curve that you are using, and you know that your critical values is 3.14, but you calculate the F values from your experiment, from the data that you have, you get 2.6. You know immediately that you have to accept H node, okay? And you go back to your alternative and null hypothesis, that if you are accepting H node, which is null hypothesis, what does your hypothesis say? And what does it mean? Okay, so that's how it goes. I have a little note down here just for those who are more interested. But one thing that I want to say is that by accepting H node doesn't mean that it is true. Okay, it is not like right or wrong. Accepting H node means that there is no evidence that we could reject it, because like I told you, doing statistic test means that you are trying the way to reject H node. You put up H node and you put up alternative hypothesis. H node or null hypothesis is something that you wanted to, that you want it, okay, that you said, okay. So you are in statistics, you are trying many ways, okay. You're trying to find evidence that it is not true. That thing is called a rare event, that it is not true. But if you can't find the evidence that H node is not true, that means that you accept that it can be used, okay, based on the statistic that it can be used. We can't reject it, okay? We can't reject it. So we have to accept it somehow, okay? But the true definition, okay? The true definition is that it is accepting H node means that there's no statistical evidence to reject it, okay? So that is the overall idea of hypothesis testing. Okay, so at this point, I think we could take a small break, and we'll come back, and I'll show you some example that I have, okay, about statistic and more on the example from the actual paper. We will talk about it next week. Okay, so we take like 5 minutes break, 3 to 5 minutes break, and we'll come back and I will continue the lecture. Okay. Recorded. Okay. Okay. Now from what we left before a little break, now I want to talked about some example of inferential statistics in scientific research. And the example that I picked out is just it's just part of the paper, not the whole paper, but I just want you to see that it could be anywhere, okay, in the type of paper that you are reading, and maybe in the results that you want to present as well. Okay, the first example, okay, is the result of a study where comparison between different treatments were compared. Okay, so if we are doing experiment like this, you probably know by heart already that the number that shows here are the average values. Okay. Oh, I'm sorry. I forgot to delete this example. Okay, this part down here. So this is not correct reference. Okay. So you probably know already that each of the number in this table are the average values. Okay. So that was part of the descriptive statistic. Okay, and some of you, when we are seeing something like this, sometimes you see the plus and minus sign as well. Okay, sometimes you see plus and minus sign as well. So, for example, for this value, you might see something like 12.64 plus minus 0.35 or something like that for each of the values. Okay, with the small letters up here. So most of you could be familiar with the sign here already. So basically, what the researchers want to do here, just to see that whether when you are doing different treatment, whether you get a different total sugar, reducing sugar, or and the glucose. Okay, so looking at the first one here says that, okay, the total sugar for the treatment one, which is control, is average at 2.55. Okay, they don't put plus and minus standard deviation here or plus or minus errors here, but when you see the letters like the C, you see these small letters here, you know that it could be compared. It is compared, so that means that you are doing more than one repeat. Okay, so the first condition give the average of 2.55 with some errors. Okay, the second treatment give the total sugar of 3.57. The third give 8.56, 8.29, and 12.64. So basically, you are comparing the mean, okay, of the total sugar between these 5 treatments. Okay. The point is, why do we have to do this? If you are doing 3 repeats, okay, these 2.55 will have some errors, right? It could be 2.55 plus and minus 0.82, okay? The 3.57 could be the average of 3.57 but plus and minus 1.10, for example. Okay, for example. So basically, when you have something like this, you want to see whether these 2 values are different. Okay, if the mean values are different, that is when you are using inferential statistics. Okay, and the statistic that compare means are the t-test. Okay, the t-test. So the t-test means that you have 2 values of the means of the average, and you want to see whether those 2 values are different. So if you are not using statistics, you will definitely say that 3.57 is higher than 2.55. So the treatment of hot water will give you a better total sugar than the treatment of the control. Okay, but when you use statistics to actually compare the mean, you see that they are not different. Okay, they are not different statistically. Okay, so you can't say that treatment of hot water giving higher total sugar than treatment of control. Okay, but you can say that hydrothermal is a different letters and you have higher values here as well. Hydrothermal will give you a higher total sugar. This is proof statistically. Okay, likewise, 8.56 and 8.29 is not statistically different. The 12.64 is statistically different. Okay, that is how you compare means using t-test. I know that many of you have used the program like SPSS, and you probably don't do the two values and compare. You compare like the whole, for example, in this one, the whole 5 values here, and you are not using just the t-test, because normally if you only compare the 2 values, okay, you use t-test because you can't do something else with that. The program wouldn't let you do it. But if you use the program SPSS and you compare these and you input this data in, most of the time you use one-way ANOVA. Okay, you use one-way ANOVA, and then you have the what we call post-hoc test. Okay, normally you do that, and you normally get 2 tables, and you could use LSD or LSD test, least square difference, or you could use Duncan test, and it will tell you which value is not different and whether it's different from the next values. Like you can have a more complex thing like this case here, okay, where you have the BC and C and B and BC and A. Right, so that's how it goes with the with comparing the means. Okay, these things are achieved by using inferential statistics, by using the t-test. Okay, so that is one of the examples that you will see a lot in the paper that you read. Okay, going on to the next example. Okay, this is also very popular in our field. Okay, so in this example, the researcher want to see what factors actually influence the response. Okay, and in this particular study, they use Takeuchi design to determine the factors that influence the response. And it doesn't have to be Takeuchi to do this. You can use CCD, of course. In the next example, we have that, or you could use a full factorial design, or you could use 2-factor factorial, 2-level factorial design, or any other experimental design, maybe in response surface methodology, to determine what factor is affecting what. And those design, okay, and the program itself, okay, for this one you could use SPSS if you are familiar with that, or you could use Design Expert. Okay, so what they always give out is the analysis of variance. Okay, so by looking at this, you know that the response that this researcher is interested in is the ethanol production. Okay, so ethanol production is the response. And by looking at this, okay, you know that there were 6 factors. So it's recombinant cellulase, that's 1, hemicellulase 2, Saccharomyces cerevisiae, Candida shihate, pH, and temperature. So there are 6 factors. So basically, what researchers wants to do is they want to see which of these 6 factors affect the ethanol production, which is the response. So they are doing Takeuchi design. So the program, you have the tables to see how you set up the experiment with the Takeuchi design, or if you use the program, they decide the experimental run for you. But what I want you to see is that what they calculate is the F values, okay? What they calculate is the F values. So you know that this one is F distribution that they are using to determine the effect of factors, okay? And if you have some basis of F distribution, you know that you can find F critical by, you can find the F critical if you know the alpha that you use, you know the DOF1 and DOF2, okay? And DOF1 being this, DOF2, DOF2 is DOF of the error. So this is how it goes with the F distribution, and it's the way to find the F critical. But most of the program, apart from the F, they actually give you the P values already, okay? The P values already. And for example, if this one, the alpha that this guy wants to do is 0.05, so you just compare the P values that they use with 0.05. If it is more than 0.05, you conveniently say that that factor is significant, so it has the effect on ethanol production, okay? This is like skipping the step. In this case, okay, in this case, edge node being that using different amount, for example, this one, using different amount of cellulase, okay, will not make the difference in ethanol production. That is the edge node, okay? And alternative hypothesis is something else. So basically, when you have the P of 0.54H, which is far higher than 0.05 here, some program will say it's insignificant. So that means that adjusting the level of cellulase doesn't affect the ethanol production, because it's doing so, you accepting H node, okay? Because P value is higher than 0.05. Accepting H node, it means that changing the level of cellulase doesn't change the amount of ethanol being produced. Whereas pH, you see, the P values is smaller at 0.0148, which is smaller values than 0.05. So the area, okay, of the tail is within the rejection area. Okay, so if the area, okay, I'll just put it in here. This is the F distribution curve, and this one said the area here is alpha 0.05, so that means that it is 5%. So this one is more or less 1.48%, which is probably around here, 1.48%. So that's when you are rejecting H node, okay? You're rejecting H node means that changing in temperature would make change in ethanol production, because you're rejecting H node, because your H node saying that changing the pH level doesn't change the amount of ethanol produced. Okay, so that's how it goes. That's how it goes. So in this one, you see that you are doing testing. The total number of hypothesis tests that you are doing in this one is 6 hypotheses, 6 tests that you did this one. The first test to see whether changing the level of cellulase will change the ethanol production. Changing level of hemicellulase will change the amount of ethanol produced. Also with the rest. So if you understand this stuff, I mean, whether it's changed the way you interpret the data, it doesn't change. I mean, because you know the result already, but by doing so, you understand why they are making conclusion like that. Okay, and this is simple because it is something that we have already known. But if it is something else, okay, you probably want to see what is H node and what is HA. Okay, let's look at another example. Another example is about optimization and modeling. This is another hot topic, okay? It takes 2 slides for this one, okay? In optimization and modeling, normally what you have, okay, you want to see the optimum, right? You want to see the optimum values that give you the highest, response that you want, okay? If go back to this example, okay, this example only say that, okay, in this study, we want to see the 6 factor and see which factors has the effect on the ethanol production. But by doing this alone in this table, it doesn't say that at what level, at what values of pH, temperature, the cellulase, hemicellulase, the use of Saccharomyces and Candida, whether what values actually gives you the maximum or the best ethanol production. So for optimization and modeling, when you see this type of paper, okay, when you see this type of paper, you immediately think about what we call the response surface methodology. So it's just the way that you find the maximum values. So this example is the example from a study where various factors, okay, many factors were assessed for the effect on the response and to predict the optimum condition that gave the highest response, okay, through the use of mathematical modeling. So in this study, okay, if you're looking at this study, the equation that you see on this page is actually the equation that is used to predict the highest level of reducing sugar. So in this one, you should know immediately that there are 3 factors, A, B, and C. And in this particular paper, A is substrate loading, B is enzyme loading, and C is time. Okay, and this equation is actually is actually used to predict. The way it predicts is it's just like the calculus that you do in your undergrad. Like you have to take the slope. If the slope being 0, it could be if the slope of the y is 0, that means that it's either the maximum or the minimum. Okay, so that is the idea behind. Okay, and how we get this model is okay. Normally, the program will give it to you, but you have to choose what type of equation that you want the model to fit the data. Like for in this one, they use the full quadratic model. Okay, that's why you get all the square and the interaction between different factors. So that's a full quadratic. Okay, since the time is closed up, okay, this is how it is the ANOVA, right? It is the ANOVA that you normally see in the paper. Okay, so this ANOVA actually tells you that if the model equation could be used to fit the data. Okay, and also tells the significant level of each predictors. So this ANOVA table alone actually corresponds to the model equation. Okay, and you have R squared, adjusted R squared here. That's what we talked about in descriptive statistics. And the way they do the test is similar to before, just to see which factors are significant. But I just leave it here before we stop, that you see that they also test a test that the model is actually could be used to predict as well. So this test of the model has no hypothesis and have alternative hypothesis of itself. Okay, so knowing the hypothesis of the model testing will help you explain better than this model could be used to fit, because p-value is less than 0.05. And also another thing that you see a lot is lack of fit as well. So the test of lack of fit also has its own null hypothesis and alternative hypothesis. So that's because we normally say that, okay, if the p-value of the lack of fit is more than 0.05, so lack of fit is insignificant. So if it is insignificant, this model can be used. that sort of stuff. So if you really want to write it correctly about how the lack of fit explain the model, or how the model, the testing of the model is actually what is itself. So it's it will be very useful, and it will make your study more meaningful in that way. Okay, I'll take the whole time for this lecture. I'll see you on Monday. I'll take any question that you have. If you come across this paper and you don't actually understand or want some guidance on it, and we will go through some papers, some example papers, just to show you that how the statistics that we do actually get involved into the study and the research in biotech. All right, okay, thank you. Thank you everyone. And also next time that we see each other, for Thai students, you could definitely ask in Thai. I will answer in Thai, and I will answer in English as well if I see that question could be useful for our friends also. So prepare your question in Thai. You can ask in Thai. I know is better. Okay, I know that is better in our case. All right, so that's it for the lecture today, and I'll see you on Monday. All right, so Thank you, everyone. And yeah, you can leave the room as you wish. And I'll see you on Monday afternoon. That will be our last lecture. Okay. That's prepare a question that you want to ask. Thank you. You can leave the room. I'll leave the room open for a little bit.
ขอบคุณครับ